Section 2.7, prove angle pair relationships. We're going to use angle pair relationships and prove theorems that with two-column proofs. So here's the first one. The right angle congruence theorem says all right angles are congruent. Well, that makes perfect sense. Of course, they're all 90 degrees, they're going to be congruent to each other. But we can actually prove this using a two-column proof. So we're going to make our two columns for statement and reason, and we're going to start numbering. Okay, so it says given that angle 1 and angle 2 are right angles, so we're going to write that. Angle 1 and angle 2 are right angles, and that is given. Again, notice that almost always the first statement we're going to write is our given statement. So then, what does it mean that when we have a right angle? Well, if we have a right angle, that means their measures are 90 degrees, so we're going to write that. That means the measure of angle 1 is 90 degrees, and the measure of angle 2 is 90 degrees. Why? Well, I just said, because that's what it means to be a right angle. So that is definition of right angle. So it's obvious from here, but how do we actually write this proof? Well, we know that the measure of angle 1 equals 90 degrees, and we know that the measure of angle 2 is 90 degrees, so we can substitute what 90 degrees is equal to in for 90 degrees, which gives us then that the measure of angle 1 is equal to the measure of angle 2, and that is by substitution. And now we just have one kind of picky detail. Again, these are very similar statements, but because the measure, notice we're trying to prove here that angle 1 and angle 2 are congruent. We haven't proved that. We've proved the measures are equal. Well, that's what congruence means. So our final step to actually prove this is to state that angle 1 then is congruent to angle 2, and that is by what definition of congruent angles means. So again, now we have proven, okay, our right angle congruence theorem. So let's talk about another theorem. This is the congruent supplements theorem. And it says if two angles are supplementary to the same angle or congruent angles, then they are congruent. So we are going to try to prove here that angle 1 right here is congruent to angle 3. And we're going to do that using the fact that we are given that angle 1 and angle 2 are supplements. So here are our statements and reasons. So we are given that angle 1 and angle 2 are supplements, and 2 and 3 are supplements. So we're going to write that. So angle 1 and angle 2 are supplements. That means they're supplementary. And angle 2 and angle 3 are supplements. We could write two different statements for this, but we could also include it just on the same statement. And that is, again, our given statement. So now, what does that mean when they're supplements? That means that when you add those angles together, the measures equal 180 degrees. So we're going to state that. It's obvious, but we have to state it in our proof. So we could say then that the measure of angle 1 plus the measure of angle 2 is equal to 180 degrees. And with the other pair, we could also say that the measure of angle 2 plus the measure of angle 3 is 180 degrees. And that is by what definition of supplements means, or definition of supplementary. Okay, so we've got that part down. Well then, notice that we could notice that 180 degrees and 180 degrees. So we can substitute what 180 degrees is equal to in for that 180 degrees. So then that leaves us with the measure of angle 1 plus the measure of angle 2 is equal to the measure of angle 2 plus the measure of angle 3. And that reason would be substitution. All right, well, we're close, but we've got a little bit more than we need. Notice, these are the same. So we can actually subtract the measure of angle 2. We normally wouldn't put this in our proof, but just so you can see what we're doing. And if we do that, we get that the measure of angle 1 is equal to the measure of angle 3. And that is by the subtraction property of equality. And now we're close, okay? But this isn't quite there. This says the measures are equal. We want them to be congruent. Well, we know that that's pretty much the same thing, but we are going to actually say, since the measures of the angles are equal, then that means the angles are congruent. And that is by definition of congruent angles. So now again, we have actually taken and we have proved this. All right. So we had the congruent supplements theorem that said if two angles are supplementary to the same angle, then they are congruent. Well, what about if they're complementary to the same angle? Well, it's really the same thing. So I'm going to let you try to see if you might be able to do the similar proof right here, but change this to complements. And basically, you're going to write the same proof, but instead of using 180 degrees, you would use 90. So go ahead and give that a try, and then, so go ahead and try to do that using the same given statements, except insert the word complementary for the complements theorem instead of supplementary. These are kind of interchangeably for these theorems that will work the same way. And then check back and see if you have gotten even close to the proof. You can check the notes later on. All right, there is a linear pair postulate here. And again, postulates don't need to be proven. They're accepted without proof. And the linear pair postulate says, if two angles form a linear pair, then they are supplementary. So again, we don't need to prove anything. We just need to know that these two angles will add up to 180 degrees. Supplementary means they equal 180 degrees. So they add up to 180 degrees. But we can use that as one of our reasons or justifications in our proof. Okay, here's one more. Okay, this is the last of our angle pair relationships that we're going to prove, and then we're going to do one more additional proof. All right, vertical angles congruence theorem says that vertical angles are congruent. We've already stated that theorem. Okay, you've already been using that theorem, but let's go ahead and let's prove it. So again, we start with our two-column proof with two columns, with our statements and our reasons, and we number these. So it says given angle 1 and angle 3 are vertical angles. Okay, and that is given. So what does it mean when they're vertical angles? Well, that means they're across from each other. And we already know that they are congruent to each other. But what else could we use to prove it? Okay, we already know it's a theorem, but how could we prove this theorem? Well, we can see that angle 1 and angle 2 form a linear pair. So angle 1 and angle 2 are a linear pair. Okay, how do we know that? Well, because it's given from the diagram. So it's given or marked from the picture, and by definition of linear pair. Okay, well, likewise, okay, also angle 2 and angle 3 form a linear pair. That's maybe not the best color to use. So angle 2 and angle 3 also form a linear pair. Okay, and again, I'm using the same reason for both of those. I could put those on 2 different steps. That would be fine. All right, well, what did we learn about linear pairs? Okay, well, we learned back here that if two angles form a linear pair, they are supplementary. So we can go back here now. We can say that angle 1 and angle 2 are supplementary. And so are angle 2 and angle 3. Okay, and we just scrolled back to see the reason we can say that is because of the linear pair postulate. Okay, well, then we can go back and scroll back as well. If two angles are supplementary to the same angle, then they are congruent. So scroll back. That's our congruent supplements theorem that we just proved. If two angles are supplementary to the same angle, then they are congruent. So I can actually jump to saying that angle 1 then is congruent to angle 3. And the reason is the congruent supplements theorem that we already proved. So remember, you can use other theorems that you already have as reasons and justifications in your proof and to prove different things. So those were kind of simple proofs, but sometimes simple ones are actually more challenging. This is one of the reasons it's so important that you have all of these theorems and proofs in your notes so you can refer back to them to do new proofs. We're going to try one more, a little more challenging proof right here, where we are going to show that the perimeter of ABC is equal to the perimeter of ADC. And again, we're going to kind of get rid of this explanation column at this point. And we are going to write our statements here and our reasons. All right, so the first statement I am going to make is that side AD is equal to side AB. So AD right here is equal to AB. And I'm also going to say that side DC is equal to BC. Okay, and the reason that I can say that is because it's given in the diagram, or we could say marked that way. All right, so now we also know that AC right here is equal to itself. So we're going to say that AC is equal to AC. And why? There's your reflexive property. All right, so now let's take this statement, AC equals AC, and let's add an equal amount to it. So I'm going to take that AC equals AC, but I'm going to add an equal amount. I am going to add AB. Doesn't matter what I add as long as it's an equal amount. And that's a true statement because of the addition property of equality. You can add equal amounts to two sides that are equal and you'll still have equality. All right, so now I could use some substitution here. And what I could do is, since AB right here is equal to AB, I could substitute what ADB is equal to in for AB. So since AD is equal to AB, I can replace this second one right here with AD. So then what does that give us? Well, what it gives us then is it still gives us AC plus AB is equal to AC plus AD. And that is substitution. Okay, well, now I have these two statements, and I could still, again, I could add an equal amount to each side. So I'm going to take this original amount here that I had, the AC plus the AB, and the AC plus the AD, and I'm going to add another equal amount. And sometimes this gets kind of tricky. What are you supposed to be adding? But in this case, I am going to add DC. And that is, again, our addition property of equality. Now, you might be saying, how do you know which things to add? Well, I'm trying to get the perimeters. Okay, and so when I'm trying to get the perimeters, I'm trying to get these three all together, added together. So I have AC, actually, right now on this side, I have one of the perimeters already. I have AC, AD, and DC. So I actually have this perimeter right here, right there. Okay, so that's one of the things I was trying to get. But the other side doesn't match the other perimeter over here. This is AC, which is this right here, and AB, which is this, but I need not DC, I need BC. Well, again, I could use substitution because, find a different color here, because DC is equal to BC, and here's a DC, I can put that BC in there, and that's the side that I needed over here for my perimeter. So now what I have is that AC plus AB plus DC is equal to AC plus AD plus DC. And again, that was substitution. And so now if you look at, again, this perimeter right here, AC, AB, DC, that is this right here, AC, AB, and BC, DC. Oh, I forgot to put in the BC. Oops. Remember, I was supposed to replace that with BC. And I actually forgot. So this is BC. And that is the other piece of the perimeter that I need for this yellow triangle right there. And now this perimeter is the orange triangle. And so now I really can sort of, through obvious fashion, or maybe we could use more steps if you feel it necessary, but we could say now that the perimeter of A, B, C is equal to the perimeter of ADC. So ADC, I have these backwards, I guess. Here's ADC, and here's ABC, but those are the correct perimeters. And it's really kind of the same thing. They're equal to each other. It doesn't really matter which side of the equal sign they're on. If we wanted to, we could flip-flop them around using the reflexive property. But that's by definition of perimeter. And we can say substitution. And some of these proofs are kind of challenging. I don't expect you to be able to do them on your own yet. But it's really a good idea to go back and practice some of these proofs that we've done. and try them again on your own, and then watch the video for the explanation or check the notes. But this is the end of our 2.7 lesson.